How are you, everybody who is watching this video? My name is Olenjolai single from beautiful, fantastic country, United Republic of Tanzania. I'd like to welcome you into a fantastic country. Welcome. If you have never come to Tanzania, you are warmly welcome. I'm very happy to welcome you once again in our online institution that's called Online Undergraduate Polytechnic Institute of Tanzania, in square bracket, OLENJOLAIM. Okay, and then simultaneously, because I know that we are mathematicians, so when I speak about simultaneous, you have been solving about simultaneous equations. I would like to welcome you into our official YouTube channels that's called Online Undergraduate Poly Institute of Tanzania, in square bracket, also OLENJOLAIM. Okay, I would like just to remind you quickly the vision that we have in this platform or in this institution, so that we can go on with the lecture, lecture 2 that I've written there. Is it lecture 2? Can you write the lecture number? Okay, so, okay, all right, it's lecture 2 of, yes, this lecture 2 for this concept or for the topic of the series. Well, this is the vision. If you ask me, Olenjolai, what is visions? If you ask me this question, that Olenjolai, what is your visions in Tanzania, in Online Undergraduate Polytechnic Institute of Tanzania, in square bracket OLENJOLAIM, then this is the answer. Well, the vision that I have, I received it from my Father who is in heaven, who gave me these visions long time ago, and he has been processing slowly until to the state that I say, let me take procedures. What he revealed in me, he revealed in me that he wants to see a special group of continuing and graduate students who are ready to take the classroom instructions in mathematics, science, and engineering and combine it with the knowledge and wisdoms of the Word of God from the Bible in order to solve real life problems. That's the visions, that's all. It's something which seems like a complex, because you know that combining, it means that we say the physical or the nature knowledge itself is complex, and also the knowledge of the Word of God, that's another kingdom system, right? So it seems like it's difficult, but it is difficult because we have been believing that it's difficult. I'll be processing this idea in your mind slowly. It's not just like within one session, then I will achieve. It's a process. It's a lifetime process. It's a gradual change, but it's a radical change. We have some specific objectives that I'll let just to quickly remind you. One of our specific objectives to help our students will be taking these programs as supplement to their classroom instructions, especially for engineering and scientific mathematics, higher engineering and scientific mathematics. Then this is higher engineering. So the department is called the Higher Engineering and Mathematics. This basic mathematics is for the diploma students. Also that you can watch. We have some other official YouTube channel which we train students, and the vision is still the same. So that is for higher engineering and scientific mathematics. So this is the supplement, because they will be going to the classroom, and these are the material which will supplement their process of learning. So our specific objective, we want to help you to pass all your continuing assessment and even university exam, right? So the name, welcome. We have some departments in this institution. One of the departments is called the Higher Engineering and Scientific Mathematics, right? So the module or the course is Differential Equation and Complex Variables. So I say that this is the common modules for second year undergraduate students, and these contents may be used elsewhere in the world, but our primary focus is by using the curriculum and the syllabus of United Republic of Tanzania, where we have two types of institutions, types of authorities that are accrediting the institutions, colleges, and universities for higher educations. We have NACTE and we have the TCU. So there's a lot of information which I can provide you in these introductions, but just that's a brief, in case you want to get a review. Okay, so we say that this is quick review. What the meanings of quick review? The meanings of quick review, this is a technique God has given me more than 11 years ago, just to, I think more than 7 years ago. Okay, quick review of lecture, to link my lectures or my sessions. So in case you want to know more about what problems are we solving, how are you going to challenge you, what a big picture in your mind about engineering, higher engineering and the scientific mathematics, and then what are the reference books that you need in order to learn this module or course of differential equation complex variables, and that's what are the topics, right? So you have to make sure that you watch this lecture 00. I've explained in detail for more than an hour. So that's the point. So again, we have another lecture in our YouTube channels that called lecture 01. And here just we had made basically we introduced to you the terms we call the series. But before series, just introduce to you first of all the terms on your sigma notation. So what is sigma notation? So sigma itself, before even defining the concepts of notation, it's a Greek letter, right? It's a Greek letter. And this is the uppercase of that Greek letter. We have a lowercase, which is the one that we use to notate the standard deviation. So this is lecture or session 2. Okay? So that is, so we said that we have the sigma notations, and then we touched about 30, another sigma notation. This is the uppercase, and this is the lowercase. Okay, this is used in statistics, this is used in series. And then I taught you about types of series. We say that we have two mainly types of series. We have infinite series, and then we say this one, it has a first term, it has a middle term, and then the last term will be infinite. And the second one, we say that in power series solutions, we need 30 types of series. Then we have finite or infinite series. So finite series, we have the first term, we have the middle terms, right? And also we have the last term, so it's known. So this is the finite series. So, and then we define about the meanings of sigma notations and provided some examples, etc., etc. So today, let us go in lecture 2. I would like just to teach you about that concept called the index and shifting of the index. So the two concepts. I will teach about index, and then I'll be teaching you how we can shift to the index. Okay, and then I will show you the maneuvers. Don't get confused about that. And this is still the first topic of series. We haven't started the power series yet. Okay? So we say that, first of all, the fundamental questions of Sir Olenjolai, once I teach something new to my students, I used to ask this question myself during the preparation. What is index? And then when you say index, what is indexing in sigma notation? Okay, sigma notation. Sigma notation, and you have to against the limit of 40 of power series, because we have sigma notations also in general algebra. So I don't want to focus on that. We are focused on the power series. Okay, the power series. So we say that sigma notation, we say, is the positive integer, right? Integer, integer, which is used to count, okay, terms, and they list and give the list and give the appropriate list of terms, okay, of the series. The series expressed in sigma notation. Okay, I said again the reference syllabus and curriculum for these modules, which I'm using as just like a reference syllabus, is Dar es Salaam Institute of Technology. Dar es Salaam Institute of Technology. We teach this module to the second year student in first semester. So this is the definition of the index. So it's a positive integer which perform mainly two activities. The first activity, it counts the number of terms, and also the second ones, it gives the appropriate list of 40 of terms of the series expressed in sigma notation. Right? So does it make a sound for you? Okay, so what does it mean? So mathematically, for instance, okay? So mathematically, what do you mean? When you talk about index, we talk about integers, right? Integers. Of course, okay, we have some value. For example, here I can have n as represented in that list of integers. N is equal to r. And then here the last term, let's say, is 5, right? And then here we have a certain n stem, right? N stem formula. Here we have n stem of the series, right? But this n stem also, it can comprises. So you see, for example, this one, this we call the counting index. Counting index. So it can help us to count the number of terms. Even this one, also we call it counting what? Counting index. It gives us information to know the number of terms. But when it comes to the n stem also, this n stem, right, of the power series, n stem. So n stem, we say that it comprises what also? Comprises subscript, and what? And superscript index. And this superscript index, we call them summation index because they are inside the sigma notation. So what does it mean? For example, you can find an example, the n stem of the certain series, the n stem is equal to a, and then we say that a n, and then say we have x power n. So this is the subscript index, and this is the superscript index. Okay? So if we express in our sigma notation, for instance, right? If we take that example, so we say that now, the general example. Okay? So the general example can say that, suppose the last term here is 5. The series comprises only 5 terms. The first term here is when n is equal to 1. So we have here that an, and then we have what? xn. So this term and this term, we call them formulating 2 types of counting index. And this term and this term means that this subscript and superscript formulating, and even sometimes we can find that we can have n here, right? Means that a certain coefficient. So it means that the coefficient, it means indexing coefficient of the term or of the n stem, indexing in the subscript, and indexing in the superscript. This is subscript, so sub, and this is the superscript. These three, they formulate a new index. We call it a summation index, right? So call it a summation index. Call it a summation index. Say summation index. So don't get confused. I will give you some examples, and then we'll be enjoying. So we say that generally, before even mention types of index, generally we say that the index, right? The index of 40 of sigma notation, right? Sigma notation of a series are expressed as these are expressed as, okay, so we can have now our sigma notation, our best friend. So here we have something called the first counting index. First counting index. And also here we have last counting index, or in some of the books we call it the last upper limit counting index. And then here we can have coefficient summation index, right? Coefficients of the n stem. Again, we can have maybe a certain a variable here, which is a, and here this one we call it subscript index. So a subscript of n, let's say, plus 1. So this one, it makes, we call it what? Subscript index. And then so you can have another variable x, and here we have n. So this one, we call it superscript index. So all the three, superscript index and subscript index and coefficient index, they form a type of index. We call it in mathematics summation index. So simply we have 5 positions of the index. Okay, we have 5 positions of the index in power series. The first 2 positions is this one, the second position is this one, the third position is this one, and then the fourth position is this one, and the fifth position is this one. First 2 positions, second positions are compulsory. Steady positions, steady index is not compulsory, but for the power series, fourth index and fifth index are compulsory. Okay, so compulsory. You enjoy the beauty of engineering and scientific mathematics? Tell me in the comment section. And tell me in the comment section you're enjoying this material. Excuse me, my voice is not okay, but don't worry about that. Soon it is going to readjust itself. Okay, so if this is the case, before even, let me give you some few examples, some numeric examples now, some algebra examples. Okay, so example, we can have that. Let's say I want to give you some 2 examples before I take you into the types of the index. Okay, so we have I here is equal to 1 up to 5. First counting index, last counting index. And then here we have n plus 1, then we have a subscript of n, then we have x n plus 2. So if we analyze, as I said, what is this? This is first counting index. What is this? This is last counting index. What is this? This I call it summation, I call it coefficient summation index. What is this? This I call it subscript summation index. What is this? This we call it what? I call it what? Superscript summation index. That's all. So you have only 5 positions where you can allocate what index. So this is for infinite series. You don't expect you to have this series in power series solutions. You expect to have infinite. So for the infinite, if you want to see the examples or the allocations of index in the infinite series, then we say that this is n, let's say for example is equal to 2, and then the last term is what? Infinite, right? And here we can, as I said, that coefficient summation index might be there or might not there. Okay, and then here we have a variable a, and here suppose that we have n plus 2, and then let's say x, and then we have n plus 1, right? So you see, so it means that this one is what? First counting index. And this one is what? Last counting index. And this one is what? This is a coefficient summation index. And this one is the variable, ax, these are variables, right? These are what? Variables, which representing what? Numbers also. And this one, we call it what? We call it summation, subscript, so subscript summation index. And this one, we call it what, my dear student? Superscript summation index. That's all. So if you understand that power series solutions is becoming simpler and simpler. Why? Because we'll be dealing with this index. Yes. When we'll be solving the problems, whether we are finding the power series solutions near the ordinary point or near the singular point, so we'll be focusing on raising and shifting the index, right? So at the beginnings of the solutions, and then later on, you'll find that we can find the s terms or whatever, or maybe the special general term, right? So that's all. In case you have any question, don't hesitate to ask in the comment section of this video. As a student, Wellywide will help you, and even myself, I can help you answer your question because I love questions. Okay, so now you know the general concepts of the index. You have examples, so it means that you can write. So now you can write your own for risk because you don't know the limitations, but let me take you slowly. So if this is the case now, you know the examples of index. Can I give you some more? So it means that this is homework. So homework, means that homework equal to 0 to identify what? Identify all index, right? Identify all indices, okay? All indices. So we call them, okay, all the index. I'm afraid to say indices because it's just like, okay, all the index. I'm not sure if in plural we call them indices like in algebra, in exponentiation. Okay, in what? In the following series. So identify. So this is the third one. So we have this guy, right? Okay, and you have n is equal to 0, and then you have infinity, right? Then you have n minus 1, then x n plus 2. Simple, right? And then the first term, okay, another term. Here we have n is equal to 2, then we have, let's say, to 10, and then we have n plus 2, right? N plus 2, then you have a subscript of n, and x power n plus 1. So identify the index like what I did here. So the business I did in this second column, do it in that third column. Once you do it, you are approaching to the clear understanding of the power series. Because I would like to insist to you, everything that I'm teaching you in this fundamental stage, we are going to use it in solving problems. So please, I beg you, take this material seriously. Because I have been teaching this module for 5 years, right? And then I was giving students quizzes in the class so that it would test their understanding before they go for the exam. What happens? I find that the students, they used to take this stuff easy at the beginnings because I used to teach sequentially. So when we get now into the power series solutions near the ordinary point, then you find that you can spend one lecture of 1 hour to solve one problem, and then even if we cannot finish. So from there, because we've been employing now the combinations of the concepts we've been learning in mathematics, including these concepts of indexing, then you'll find that students, they fail to understand clearly about this concept. Why? Because they ignore these fundamental materials. So it's very important. I insist you to make sure that you work on it. So then let me take you into a very interesting point, which is types of of index. Before I teach you about shifting, I want to teach you about types of indexing in sigma notation. Okay, in sigma notation, even in algebra, still we have those 2 types of index, but anyway, so let's say that in power series, okay? In power series, right? So in power series solution, so SRI, solution. So we say that there are how many? There are 2 types, okay? 2 types of index, okay? 2 types of index in power series, okay? In power series solution. Power series solution. What are these 2 types of power of index, right? So there are 2 types of index in power series solution. Okay, the first one, we call it counting, counting index. Okay, counting index. And the second one, we call it summation index. Summation index. Okay, this is the second types of the index. So you have counting index, you have summation index. Those are the 2 types of indexing we have in mathematics, or expression in power series. Say counting index, and then we have summation index. Okay, summation index. And then so we'll relate to sorting with the sigma notation. Well, So the first question we have, or should we ask ourselves as engineers and scientists, is this one. So this might be question 2 for this session. What is, so before even we ask this question, let me write the subtitle, and so I'll give you simple examples, and we keep on enjoying the beauty of engineering mathematics. So we have question 1. So I want to teach you the first types of indexing in power series, which is called the counting index. Counting index. So you have a fundamental question, right, like this one. What is counting index? What is counting index? What's counting index, right? So counting index, you say that is a type of index, right? Is a type of index which counts, counts what? The number of what? A number of terms. Number of terms where? Number of terms in the series or in the sigma notation. Okay? Number of terms of the series. Represented by what? By sigma notation. Right? By sigma notation. So that's the meaning. So simply, this is the type of index which counted the number of terms of what? Of the particular series represented where? In sigma notation. Right? That's the meaning of what? Counting index. Bear it in your mind. This is all about the higher engineering and scientific differential mathematics. So it's a little bit different from ordinary differential equations we've been solving in ordinary diploma and even advanced level. Okay. So again, if that's the case now, so it counts the terms, 1, 2, 3, 4. Remember this one indicating how many terms that the series possesses, whether infinite number of terms or finite. So then, we have again types of what? Types of counting index. Okay? Types of counting index. We have 2 types of counting index. Okay, so how many types of counting index we have? 2, right? So we say that there are 2 types of what? Of counting index. Okay, of power series summation or the series counting index. Okay, what are they? The first one, we call it first counting index. First counting index. And the second one is called the last counting index. Last counting index. So these are very important. So once I explain in brief what the meanings of first counting index and last counting index, then now I can give you the examples of those 2 types of counting index where we locate in the sigma notation of 40 of our power series solution. Do you enjoy high engineering and scientific mathematics? Tell me in the comment sections. Do you love it? Do you watch this material from which institution, from which college, from which university? Tell me in the comment sections. I'm still waiting. I'm very happy to hear you are sounding from which city, from which college, from which region, from which country, from which continent. Tell me in the comment sections because I'll be very happy to hear about that. Okay, so let us continue with these 2 types. Let me explain to you about these 2 types of the counting index. Because you say there are 2 types of counting index. The first one is called the first counting index, and the second one is called the last counting index. So let us begin with the first counting index, and then I'll represent the sigma notation so you understand. Because we have been using these indices, okay, in our computations without knowing them, so we call them indices. So first counting index. Then first counting index. First counting index. First counting index. Okay? So you say that the fundamental question is this one. What is the first counting? What is the first counting index? First counting index. That's the question. So the first counting index, we say that, simply say that is the index. So it is the index which gives, okay, which gives the first term and the middle terms, right? The middle terms by incrementing it, means by incrementing it by 1. So that's the meanings of the first counting index. In some of the books, we used to call it the lower limit of the index, right? So that's how we define in some of the books. So you have to be familiar about the definitions and even the language which has been used so that you can comprehend it well and understand. So we have different letters, but it means that it is donated. We have different letters, but the common one N, I, sometimes even J, but it's there. But in case of the power series solutions, we are going to use N as a notation. And they should be defined. This is a defining value to know where the series begin. Okay? And then we have the second one, which we call last counting index. So what is last counting index? Then I will show you in the signal notation and you'll enjoy them. Okay? What is last counting index? Right? So the last counting index, so we say that is the index, right? Is the index which gives us the last term. The last term of what? Of the series. The last term of the series. Or simply say that this gives us the end of the series. So remember that differential question for undergraduate is not a subject of stories, but I want to build a strong foundation so that we'll be enjoying the session as long as we move. So now let me present in the signal notation. As I say that, this is the point for the first counting index. For instance, that the first counting index is n is equal to 1, and our last counting index is, let's say, it is 6. And then here we have n plus 1, then we have an plus 2, then we have, let's say, xn plus 40, or xn plus 1, right? So this is what we call the first counting index. So this is first counting index, right? And this one is the one that we call the last counting index. And these are the summation index as I have explained before. So you find that. So for instance, if you want to write this series, so n is equal to 1, this is the initial or the first counting index. So for instance, this is the finite or finite series because the middle terms is known and the last terms is known. So how we can use this index to write theories? Look, because we are going also to use this technique on solving power series solution problems. So we have our n stem is n plus 1, then you have a, n plus 2, here you have x, our n plus 1. So when n is equal to 1, in every positions of n, substitute 1. So n, 1 plus 1 will be 2, so the coefficient it will be 2. Then here it will be a3, a subscript of 3. Then if substitute 1 it will be x squared. So that is the first term. We go for the second term. So as we define that, this first counting index is the index which gives us the first term, so we have obtained the first term, but also to give us other middle terms by incrementing this the initial count index by what? By 1. So now we're incrementing n is equal to 1, we're incrementing by 1. So n is equal to 1 plus 1 is equal to 2. So you substitute, right? In any position, substitute n is equal to 2. So 2 plus 1 will be what? 3. Then here, we have 2 plus 2 is equal to 3 again. So it will be what? A 3. There is subscript of 3. Then 2 plus 1 is 3. No, here 2 plus 2, which is 4, excuse me. So it is 4. Then we have what? X power n plus what? 1, but n is equal to what? To 2. So 2 plus 1 is equal to what? 3. Right? And then she said that this is plus. Then we increment n by 1. The answer is what? So if you increment n by 1, then you get it was 2. 2 plus 1 is 3. 3 plus 1 is 4. Right? And then she said what? A. Then she have what? 3. 3 plus 2, it is what? 5. Then you have what? X. X, we have 3. 3 plus 2 plus 1 is 4. Okay? So then plus. Right? So how many times you have? 1, 2, 3. How many? For the last term it is 60. When n is equal to 60. So n is equal to 1, n is equal to 2, n is equal to 3. N is equal to 4. It will be what? 4 plus, it will be 5. A 6. Then x is 5. Right? Then when n is equal to 5, the coefficient will be 6. A 7. X power 6. When n is equal to 60, coefficient will be 7, then a 8, then x power 7. This is the last term, right? So you see, how do we use? So it means that the last term will be used only to obtain the last term. The last count index will be obtained. It will be used to obtain the last term of the series. How? You take 6, you substitute here. 6 plus 1 is 7. Then 6 plus 2 is equal to 8. Then 6 plus 1 is equal to 7. So that the contributions of 40 of the last counting index in computations of 40 of the series. In case you have any question, don't hesitate to ask me in the comment section. So we are done with the first counting index and the last counting index. So we mentioned again another types of index, which we call the summation index. Right? So, ladies and gentlemen, let me present to you these terms we call summation index. Okay, this type of the index. Say summation index. So, what is summation index? That's the fundamental question for Olenjolai. What is summation index? What is summation index? So you can pause the video, ask yourself, and answer. You write down your answer, then you continue to watch the video to see the response, whether it's right or not. So simply say that this is the index, right? Index. Okay. So this is the type of index, which can be either subscript, types of index. Okay, the types of index. Expressed inside the types of indexing expressed inside the summation or inside the sigma notation, sigma or summation notation. Summation notation. So what does it mean? We say we call it summation index because we find it inside the sigma notation, right? While the first count index and last count index, we don't find them inside there. So when you say inside of the sigma notation, is this part, right? So how do you represent the summation index? Summation index might be a coefficient of the term, Maybe it's a subscript, it might be a superscript. So we say that summation index summation index may be expressed as subscript, superscript, and what? And coefficient. And coefficient of nth term. So that's the meanings of what? Of summation index. So we say it can be expressed as subscript, like this case. It can be expressed as superscript, like here. It can be expressed as the coefficients of the nth term. This is what we call the nth term, the last term. The nth, the general term, not the last term. So you see that this is coefficient summation index. This is what subscript summation index. This is superscript summation index, and this is subscript summation index. Okay, so I have already given you an example. So now you know those two types of indices, of index. I would like now to take you into another point. Okay? Into another point. So now let me take you into the last concept for this session, shifting index. Shifting index. Okay, shifting index. Okay, shifting the index. Shifting the index. Okay. So we say that in solving ordinary differential equation, ODE, the concept of shifting index, shifting was counting and the summation index, and summation index is very crucial. Very crucial or very important. So in solving ordinary differential equation of power by using the power series method, right? The concepts of shifting both counting and summation index, is very important. Very important. Very important. So that's why that we have to cover it before. Okay, in solving ordinary differential equation by using, so even here you can have by using power series method. Okay. So you say that if that's the case, you say we can shift it. So you say that we say also the concept of shifting index, right? The concept of shifting index. The concept of shifting index depend on the basic lowering an index by a certain value, a certain number, let's say a certain number or a certain value. Okay, certain value. So if we say that, if that's the case, then we have to go straight forward when we say that we are shifting. So we are going to deal with counting index and summation index. So we say that the index of counting and summation are like Idumi variables of integrations. So power series method depends on the knowledge of shifting the indices. So I say that counting is another point you have to note, and the summation indices. Summation indices are like Idumi variable of integration. Idumi variable of integration. Idumi variables of integration. What does this sentence mean? It means that if you raise the summation index, then simultaneously you have to lower the counting index. If you raise the counting index, simultaneously you have to lower the summation index. That's the means of Idumi variable. So it is the case, we say that now let us begin with the first part. We are still in series, the topic is still in series. So the first part, we say that let's say 1.2.1. So then we say that in lowering summation index, and we teach you how you can lower summation index, and at the same time you are raising counting index. You say counting index, it means about two types of counting index. However, that for the finite series, the last two terms is infinite. Counting index. Counting index. Okay? So we say that if you want to raise the counting index, we have to lower the summation index. And vice versa is true. If you want to raise the counting index, the summation index, then you have to lower the counting index. Now the means of Idumi variables of integration. So we say that there is this, the one of the property, according to properties of what? Of sigma notation. According to the property of sigma notation, according to the properties of what? Of sigma notation, we say that if you raise the counting index, you raise the counting index by a certain number, or certain value, then you have to lower the summation index by using the same factor. So that's the point you have to remember. It's a property of sigma notation. We say that if you raise the counting index, show you so, by a certain value, this is value, a certain value, right? Then you have to lower the summation index by using the same factor. So if you raise the counting index by 1, then you have to lower all the summation indices by 1. If you raise the summation, the counting index by 2, then you have to lower all the summation index by 2. When we say raise, we are adding value. It means that we are taking a certain number and then or a certain variable or a certain letter, we add it with the counting indices. And lowering means that we subtract it from the given expression. So if this is the case, if this is the principle that we need, then now we can begin dealing, or I can give you example 1 now. This is the example 1. Question says that from a mathematical book, given a generic term which is in finite series, first counting index is what? Is 2, and this is what? The field. N is equal to 2. This is A, n plus 2, x, n plus 2. Write it by using raising the summation index. They raise the counting index by 2. Now the question. Okay, so let us solve quickly this example. It's a very simple example. Should not even kick your mind. We say given a generic term of this one, this is the sigma notations, and this is the answer. Write it by raising the counting index by 2. So solution. So the first step, because you'll be following steps in solving this problem, so that we call properties of sigma notation. Called properties of sigma notation. What property? We say that if you raise, it means you take the counting index, right? Counting index. If you take this one, you add it with a certain value which will be given as 2. We say that then you have to what? You have to take the summation index, each summation index, right? Each summation index, and then you subtract it by 2. Okay? At the principle. So if that's the case now, infinity, I will show you what to do. So in these expressions, where is it? Tell me the first counting index, and tell me the last counting index, and then tell me how many summation index they have there. So pause the video, then think about yourself, then tell me in the comment section. So if n is equal to 2, raise means we are adding, so we adding 2. My dear students, I would like to insist to you that these concepts are very important in future when we'll be learning about power series solutions that we'll be using to solve ordinary differential equation. So this point that I'm teaching you about shifting of indices, believe me, you remember, you'll encounter it in many aspects more than you think. So what is our last counting index? that is infinity. So it means even this one also should add it by 2, but because it's the largest number, so simply don't even indicate. Then we come here, we have A, then you have n plus what? Plus 2. Then have x. X is n plus 2. So we say that if you raise the counting index by 2, then you have to lower the summation index by 2. So how many summation index do you have here? 2. Subscript, superscript. So here we subtract what? By 2, and you have x. Now subscript, we had n plus 2 minus 2. Right? So do your arithmetic computation and hence give me the result in the sigma notation form. Do you enjoy the beauty of engineering and scientific mathematics? Good. So if you do or if you don't, tell me in the comment section, please. So then we have sigma notation. Then we have n. 2 plus 2 is equal to 4. Last term is infinite. Then here we have a power n, x power n. And the final response. But the final response afterwards, simplification. Okay? So that's a very important point. So this is the way that you go. So we have example 2, and this is the homework for this part. Okay. So I was looking for a simple example. Homework 2. Homework 2. And this is also example 2. Homework 2 because it is in lecture 2. Okay. So, and this one we have to refer the manual. Given a generic term. Given a generic term, which is this one. Sigma notation, n is equal to 0 to infinity. And then a subscript of m plus k. This is x, n plus r plus k. N plus r plus k. Write generic term. Write generic term with xr, with x power n plus r. So these kinds of the question, but I think that let me do it because some of the students, they might think that it's a difficult question. We didn't do this type of the question. But in case also you want to make as your practice questions, so you can pause a video and then you solve once you come to correct your finding or your responses. Given a generic term of that ones, okay, so we have that this is the, what is this? And what is this? Tell me. What is this? What is this? What is this? What is this? What is AX? AX are what? Variables. Okay, so then we have to express this. We have to deal with x. X should be n plus r and should not be n plus r plus k. For this reason, because that our final expression should include x to the power n plus r, then we say that we still have that assignment. So solution. Okay? So solution, we say that according to this, the nature of a part of the elastic expression, so elastic part of the expressions, then we'll see that things are, Okay? So for these reasons, we say that this is x to the power n plus r. Where do you find x? It's within the summation or the sigma notation. So if you compare this exponent of x, the desired one, and you compare with this exponent of what? Of x, you find that there is a close relationship. So this one is just missing k, while this one contains k. So for that reason, we say that the first step, right? The first step, we say that so the first step, we say raise the counting index. Raise the counting index by 1 by k, and we lower the summation index so we raise the counting index by k and lower the summation index by what? By k. So that's what we have to do. If you are joining us right now, you're warmly welcome. My name is Olenjolai from beautiful country, Republic of Tanzania, and welcome to enjoy the beauty of engineering and scientific mathematics. And the name of the course or models that I'm teaching is called Differential Question Complex Variables. And we have two departments right now. Two departments. Okay. So one of them is that one's higher engineering and the scientific mathematics. So let us continue our expression. So we have a sigma notation here. Then here we have an infinite. Then we have n is equal to 0. This is the first counting, our first counting index. Okay? N is equal to 0. Then we have again, we say that according to this rule, when we raise the counting index by k, then you have lower summation index by k. So now, because the concept of even the question asks us to raise, that's like this. Okay? So 0 plus what? Plus k. So if that's the case, we say that if a m plus n, and say that plus what? Plus k. This is the subscript of the summation index. Okay? So this one, we have to subtract it by k. I got that principle. Okay? So, if that's the case, we have again x. Okay? We have again x. X power m plus r plus k. X power m plus n plus k. So because we raise the summation and with the counting index by 1, so even this guy here, by k, should be infinity plus k. Right? So if this is the case, what do you say? Say fine. If this is the case, you have also subtracting by k. So let us go. Okay. So then we say that here we'll be having n 0 plus k is equal to k. Then infinity plus k is equal to infinity. This is a. Then say subscript of m plus n. So we say that m plus n plus minus what? Plus k minus k. Then there we have x power m plus n. K minus k is equal to what? 0. Right? Good. So we say that now our expressions, we say that m is equal to k. K is equal to k. N is equal to k. Then you have a m plus n plus k minus k. This is a subscript is m plus n. M plus what? N. Then for this variable, which is x, similarly, we say that this guy has to remain itself as included in the question. Okay? So this is the final expression. So we have already expressed the decimal notation in generic term of 40 x power n plus r. So x power n plus 40 r. So here it's infinity plus n whatever or plus n number. The answer is infinity. Okay. Let us carry on our business. Okay. So that is all about raising the counting index and then lowering what the summation index. Now let me take you into another concept, which is 1.2.2. Say that lowering the counting index. Counting index. Lowering the counting index. Lowering the counting index. Lowering the counting index and raising the summation index. Okay, so we want to lower the counting index and simultaneously we want to raise the summation index. So again, we say that according to the properties of signal notation. According to the properties of signal notation, we say that if you lower the summation index okay, simultaneously we say that if you lower the summation index, if you lower the counting index, simultaneously counting indexing by a certain factor, a certain value. So I say that if you grade the summation, index, right? Raise the summation index by a certain value. Then you have to lower the counting index. Okay, so if you rate the summation index by a certain value, right? And then you have to lower the counting index by the same value. Okay, count index by the same value, by the same value. So let us see examples. Then give you the homework. That will be the end of this lecture too. This is the example 7. Given n is equal to 4 to infinity. To infinity. Then there we have x power n, a subscript of n as a numeric term. So you'll be given this one as a generic terms. As a generic terms. So the question said that you write the given generic term as the given generic term. Given generic. So it's a write the given generic term in x power so x power n again, okay. So x power n plus 2. So what does that question mean? So you'll be given the generic term, the general term. Then after you'll be given the general terms, you'll be given the nth term. And you haven't, you'll be given the nth term. So if that's the case, So solution. So say the first step, we said that the first step for that case, we say that check the generic term. What can you notice? It tells that the H variable, it has arisen, or it has rose, or it arisen from n to n plus 2. Right? So that's the mean. So first step, check the generic term. So we say that we raise the summation index and then we have to lower the counting index. So then check the generic term. So we say that the value of what? The value of raising or counting, raising or counting factor. Raising and counting factor is 2. You have x power n, here you have x power n plus 2. So that's the first step. The second step, we say that we have our sigma notation, then we have to deal with what you've been asked to do. So you have sigma here. So you say n is equal to 4 up to infinity, and the good news. Then you say that you have an, you have x power n. So now our intentions, we want to formulate an expressions where xe, it has plus 30 plus 2. Very important point. So it is the case you say that you want to do that operation. We lower the counting index by 1. And lower here by 1, we get infinity. Okay. So yes, so I was right that infinity plus what? 4 is 0. So you say that if this is the case, we have against our summation index, so we have to raise it by 2, and this one we have to raise it by 2. So simply say that this expression should give us what? Here the last term is infinity. Here it is n is equal to what? 4 minus 1. Are we raising by 1? No, we're raising by 2. So here it will be 4 minus 2. So 4 minus 3 is equal to what? N is equal to 2. Then you have what? Coefficients. Okay? Coefficient, as you say, that you have a, then n plus 2. We have x, n plus 2. So we have already expressed our unique terms in terms of what desired. So according to the question, we didn't focus on the arrangement. Okay? So that's the final response. So we still have couples of the examples, and I will give the homework for you, and we record them, and we'll be at the end of the session. Okay? So here it is, here is, and this is an encantment, here it is what? Example 4. This example 4, given a generic term, the question state, given a generic term, given generic term, which is similar to this, n is equal to 7. Hence, this is 11. You have a subscript of n. You have x subscript of n. Write the generic term. Write the generic term. Write the generic term with x power n plus what? Plus 3. So these are the generic terms that are. When you give us the generic terms of this, we have write the terms with x power n plus 3. Solution. What should you do there? First of all, you should compare. This is x power n plus 3. Here we have x power n. It means we have to raise the expression, the summation index by 3 in order to get this value. Okay? By 3, right? So if that's the case, you say that in fine. Well, we have to deal with this. How do you deal with this? So you say that to obtain this guy x power n plus 3, you have to, so x power n plus 3, we say that this is kinds of equivalent with x power n. So simply say that we have to raise the summation index raise the summation index by what? Summation index by 3. Okay? So when we lower the summation index, we have to lower. When we raise the summation index, we have to lower the counting index by 3 also. Okay? By 3. So if that's the case now, if we come back to our series, to our given numeric term, here we have n is equal to 7. But we want to raise the summation index from n is equal to from x power n to x power n plus what? Plus 3. So n is equal to what? 7. Okay? 7. So if this is the case, we say that here in the numerator you have what? 11. Then so what the terms? We have a power n, then you have x power n. Right? So if that's the case, we say that we want now to raise what? We want to raise this summation index by 3. And raise this one by 3. Okay? About to finish this session. So simply say that this is our numeric term with n is equal to 7 here, 11. Then we have a n plus 3, we have x or n plus 3. So then because we rate the summation index, you have to lower the counting index by what? By 3, and this one lower by 3. So this will make your summation index. N is equal to 4, right? And then 11 minus 3 is equal to 8. 8. So this is an up to 8. Then you have what? A n plus 3. Then you have x n plus 3. This is the response. Okay, that's the response, that's the final expression. Okay, so I'm looking for the homework. Okay, this is homework 2. Okay, we have this, we call it example, what? Example 5. Okay, example 5, the question says that write this, write quickly, write this generic term. Write this generic term, which is sigma notation. We have the first counting index is n equal to 2. The last one is infinite, as usual. Then the summation, the n stem now is expressed as x power n plus 2. Then this is expressed by x power n minus 3 plus what? Plus 1. Okay. And then I multiply with x squared. There's x squared minus x naught out for n minus 2. So x power n plus 2, then open bracket, x power n minus 3 plus 1, then x squared minus x 0, n power n minus 2, then with what? So with x squared minus x naught power n. So deal with the given generic term, and then after we have dealt with that generic term, finally you have to make sure that you write one of its term in terms of what as x squared minus x naught power n. At the first question, we may give you the second one, then this will be the end of this session. So make sure that you do it and submit in the comment. So this is example 6. Yes, example 6. So example 6 is concept. Have to be careful. Write the given generic term write the given generic term okay. So write the given generic term in what? In generic term. Make sure to do this homework before we meet in the next session. Okay? In generic term with export x power n. So our generic term here, it is x power 4. h power 4, n is equal to 2 to infinity. Then we have n times n minus 1, then a subscript of n, a subscript of n, then so you have what, x power n minus 2 plus what? Plus x square plus x square, a subscript of n, x power so a n x power n. So it's x power 4 summations from n is equal to 2 to infinity, n times n minus 1, a subscript of n, x power n minus 32. Then plus what, x square, simultaneous a n x power n. So make sure that you do that questions and then let me know your solution. This is n is equal to 0. N is equal to 0. Okay, when n is equal to 0, and this one is to the c motive, to infinity, the infinity point. So this the expressions, the same expressions, the same generic term. So express x power n, now x2 minus x0, and square bracketing is the one of the given expression. So this is the given expression, and at the end of this lecture, lecture 2 of index and shifting of the index. So I thank God who have been with me during the preparations of this lecture. I thank God who have given you an opportunity to join me and to learn this stuff. And I thank God because He has given you a chance to learn digital, which actually that I haven't got this chance to learn the materials focusing on the syllabus and curriculums of United Republic of Tanzania. I just remind you, make sure that you subscribe, because in this channel we are going to add more than hundreds. We'll be adding hundreds videos. And the good news also, we have some other modules or courses for other institutions or universities. So read also the descriptions of this video, subscribe. Remember to subscribe, and then you choose the options of all, so you get notifications once we add a new video. So it means that you won't get lost along the way. So may God bless you abundantly. I'm always praying for you. I'll be keeping praying for you. I ask you also to pray for me so that God may give me strength so I may do this business effectively. So really may God bless you and keep you until we meet in the next sessions, which is lecture 3. So be blessed.